Welcome to AI Paper Slop. We are jumping straight into a June 2026 paper today from researchers at Tsinghua University and Tencent.
Yeah, a really fascinating one.
It's titled Trace, a unified rollout budget allocation framework for efficient agentic reinforcement learning.
Right.
And let's just get straight to the core insight here. Reinforcement learning with verifiable rewards, RLVR, is computationally massive.
Oh, absolutely massive.
Right, and right now, most scalable pipelines use these binary outcome-only rewards, which, provide terrible, incredibly sparse signals. Trace solves this by intelligently allocating your rollout budget.
It's a completely different approach.
Exactly. Instead of just filtering prompts, Trace dynamically branches at midterm prefixes. It basically hunts down those specific thought-action-observation nodes where the outcome is most uncertain.
Yeah, the high variance forks in the road.
Right. And by targeting those forks, Trace generates rich contrastive preference pairs without increasing your sampling budget. This significantly boosts policy optimization for agentic LLMs like Qwen 3.
It really does.
So, if you are spending thousands of GPU hours on GRPO or tree-based RL, this paper completely redefines where you should be spending your inference budget during training.
It forces a total rethink of rollout geometry, honestly. To really grasp why Trace is such a breakthrough, we have to look at the structural failure of the current RLVR paradigm for multi-turn agents.
Okay, let's unpack this. What exactly is failing?
Well, historically, to get a model to reason, you want process reward models, or PRMs. You want a system that evaluates every single step of a long tool calling trajectory.
Which makes sense in theory, right? Step-by-step feedback.
Right, but training a robust PRM requires massive amounts of human-labeled data, which just doesn't scale at all.
No, not even a little.
Or, if you try to automate the PRM, the policy model quickly learns to reward hack the intermediate scoring rules without actually solving the underlying problem.
Oh yeah, the classic reward hacking issue.
Exactly, so that forces the entire industry to rely on outcome reward models, or ORMs.
Which basically means we are just looking at the terminal state. Like, did the Python script compile and pass the unit test?
Right. Did the math equation evaluate to the correct string?
Yeah, it is just a binary 1 or 0 at the very end of the line, which leaves the optimizer with an incredibly weak signal.
It creates a massive credit assignment crisis. Let's ground this in how Group Relative Policy Optimization, or GRPO, actually works under the hood.
Since that's the engine for a lot of these models right now.
Exactly. It relies heavily on having a group of outputs to compare. If you pass an agent a prompt and it generates, say, 8 different trajectories, GRPO needs some of those to be successful and some to be failures to calculate a relative advantage.
Makes sense. You need contrast.
Right. But now, imagine a 15-step trajectory. The agent uses a search tool, reads a document, writes a Python script, gets an execution error, writes a fix, and so on.
Right, a standard complex task.
And at the very end, the environment just hands back a terminal 0. The optimizer is left completely blind.
Because it doesn't know what went wrong.
Exactly. Which specific tool call or thought was the fatal mistake? Was the initial search query bad, or did the logic fail at step 14? Outcome-only rewards just don't tell you.
It's like forcing an agent to play an entire 50-move game of chess, and the only feedback I get is, you lost at the end.
That's a perfect analogy, actually.
Right, and the optimizer is expecting the model to magically deduce that its 4th move was the actual blunder, while the remaining 46 moves were just the inevitable fallout.
Yeah, and the problem compounds when you look at the prompt level. If a prompt in your training dataset is simply too easy, the agent will succeed every time, returning a flat line of 1s.
And if it's too hard, it returns all 0s.
Exactly. In both cases, the generated rollouts have absolutely 0 outcome variance. They give GRPO no comparative data. The relative advantage calculation just flatlines.
Which means those thousands of generated tokens are essentially wasted compute.
100% wasted.
But wait, hasn't prior work tried to fix this? Like, the obvious engineering fix here is to just filter the dataset. Methods like prompt curriculum learning, or PCL, have been doing this.
They have, yeah.
They train a predictor to score the difficulty of a prompt and just throw out the ones that are trivially easy or impossibly hard before you even spin up the GPUs. Right?
PCL does attempt exactly that, yes. But Trace identifies a fatal flaw in that approach. Prior work only filters at the prompt root.
Meaning the very beginning of the generation.
Right. Once a prompt is selected from the pool because it has a supposedly good difficulty, the rollout is still generated blindly as one atomic flat trajectory.
Ah, I see.
that completely ignores the rich semantic variation happening inside the multi-turn steps. The prompt might be perfectly challenging on paper, but by step 8 of the trajectory, the agent might have stumbled into a state where success is suddenly guaranteed.
Or where failure is suddenly inevitable.
Exactly.
Hmm.
And generating the rest of the trajectory as a flat line from that point forward is still wasting compute.
So prompt level filtering is just treating the symptom, not the disease.
Bingo.
Which brings us to the core theoretical breakthrough of trace. We have to shift the allocation geometry from these flat atomic trajectories to tree-structured prefixes.
Yes, we need to look inside the trajectory itself. And this is rooted in the math of uncertainty.
Okay, lay the math on me.
So trace introduces the concept of mixed reward contrast construction. In RLVR, the goal isn't actually to get successful rollouts.
Wait, really?
It's not.
No, the goal is to find anchors, which can be prompt roots or intermediate prefix steps whose descendants will yield both successes and failures.
Oh, I get it. To create that contrast for GRPO.
Exactly. When the tree-aware optimizer sees two branches diverging from the exact same prefix, and one leads to a 1 while the other leads to a 0, it gets an implicit pairwise preference.
It finally knows exactly which local decision caused the failure.
Yes. It solves the credit assignment crisis completely. Here's where it gets really interesting. If you think about how this actually plays out, it's a lot like reading a choose-your-own-adventure book.
Oh, that's a great way to look at it.
Right. Like, if you want to map out all the different endings, it would be a massive waste of time to reread the entire book from page 1 over and over again, making uniform, random choices.
You'd be reading the same intro 100 times.
Exactly. So Trace doesn't do that. It finds the exact page where the hero's fate is mathematically 50-50, and it spends its compute reading just the alternative choices branching out from that specific page.
And the authors back that intuition up rigorously in Proposition 2 of the paper.
Okay, what's the formal proof look like?
They define the variance of a Bernoulli outcome as V times 1 minus V, where V is the conditional success probability at any given node.
Okay, V times 1 minus V.
Right. And they prove that this isn't just a static measure of uncertainty. It represents the expected accumulated movement in conditional success probability below that prefix.
Let's break down that formula for a second so I'm following. If a lightweight predictor looks at a partial trajectory and thinks the model has a 99% chance of success at step 4, V is big 2.99.
Correct.
Multiply that by 1 minus V, which is 0.01, and you get a tiny variance of 0.0099, meaning branching from that node teaches the optimizer almost nothing because the outcome is effectively locked in.
Exactly. But if V is 0.5, then 0.5 times 0.5 gives you 0.25, which is the maximum possible variance.
Ah, so that's the sweet spot.
Right. That specific prefix is highly likely to yield opposite terminal outcomes if you allocate your compute to branch from it. What's fascinating here is how incredibly elegant this is for the gradients during training.
How so?
By fixing the past context, the entire prefix history up to that 50-50 point, and only varying the future continuation, Trace guarantees that any difference in the terminal reward is strictly due to the new continuation.
Because everything before that point is identical.
Exactly. It isolates the variable. This feeds tree-aware optimizers, like tree GRPO, perfect local credit assignment without ever needing humans to write process reward rules.
Okay, the mathematical goal makes total sense. We want to hunt down that V times 1 minus V sweet spot.
Yes.
But looking at the system architecture, doing this dynamically sounds like an absolute nightmare for parallelized LLM inference engines.
It does sound like it would break everything.
Right. Because standard pipelines like VLLM rely on continuous batching and predictable sequence lengths. If we are constantly stopping, evaluating intermediate nodes, and spawning new branches, how does Trace avoid creating massive bottlenecks?
The architecture is specifically designed around those hardware realities, using a two-stage initialize then expand pipeline.
Okay, what's stage 1?
Stage 1 is global root allocation. The system looks at a massive candidate pool of prompts. It uses a shared, very lightweight predictor model, which they denote as V tilde psi, to estimate the success probability of each prompt route.
Got it. Just a quick scan of the pool.
Right. Trace then uses a dynamic programming solver to assign a budget, Y, to each prompt. This solver is essentially optimizing a knapsack problem.
Like, how do we maximize the expected contrast across the entire dataset given a fixed total token budget?
Exactly that. The vast majority of prompts are simply assigned an M of 0 and skipped entirely.
Because they're too easy or too hard.
Right. But prompts with high contrast potential are assigned a budget for multiple bare rollouts. These are full, flat trajectories just to explore the space and gather initial data.
So stage 1 handles the prompt filtering, but it's doing it with an eye on the total system budget, is letting the agent lay down some initial tracks.
That brings us to stage 2, local prefix expansion.
Okay, this is the dynamic part. Yeah.
Once those initial bare rollouts finish for a given prompt, Trace looks at all the visited prefixes. Remember, these are the intermediate histories of the thoughts, actions, and observations. The exact same lightweight predictor evaluates these intermediate nodes. This predictor is trained on historical trajectory data, so it knows how to map an intermediate state to a terminal reward probability.
And then it allocates the branches.
Exactly. Trace then allocates its remaining budget, the continuation branches, to the specific prefixes that are most likely to flip the observed reward.
Oh, wow. So if a bare rollout ended in a 0...
The system looks back through the trajectory for the node with the highest probability of turning into a 1 and spawns new branches right from there.
But wait, this is where the hardware bottleneck usually happens. If we are dynamically expanding trees based on what happens in the middle of a rollout, doesn't this cause massive straggler delays?
You'd think so, yeah.
Like you'd have GPUs sitting idle on one worker node just waiting for other prompts to finish their bare rollouts on another node so the global allocator can decide where to branch next.
That would absolutely stall the cluster if the prefix expansion was a global operation. But the authors avoided that with a strictly prompt local design in stage 2.
Oh, prompt local.
Yeah. The initial bare rollouts for a specific prompt are co-located on the same worker node. Because of that, the expansion is enqueued immediately upon their return.
So it's totally asynchronous from the other prompts.
Exactly. The system doesn't wait to see what happened with prompt B on worker 2 before expanding the prefixes for prompt A on worker 1. It completely bypasses interprompt waiting across different workers.
That keeps the inference engines fully saturated. Oh, I see the implications there.
It's very clever engineering.
And because they are branching from midterm prefixes locally, they can exploit the KV cache.
Oh, absolutely. That's a huge part of it.
They don't have to recompute the prompt and the first half of the trajectory for every new branch. VLLM uses paged attention, so they just hold the shared prefix in memory and only compute the new tokens for the diverging continuations.
Exactly. That makes the branching virtually free in terms of memory footprint compared to starting independent trajectories from scratch.
That KV cache sharing is a massive component of why this is actually feasible at scale.
It allows Trace to build these dense, localized trees without exploding the memory budget.
Okay, so the theory isolates the gradient perfectly, and the system architecture respects the hardware constraints of distributed chaining.
Right.
But, theory is cheap. When you actually force an agent to solve unseen problems using this pipeline, does the math translate to actual intelligence?
That's a real test.
The paper tests this across 3 rigorous agentic benchmarks. We have mathematical reasoning using the deep scalar corpus, tested on AME 24 and Math 500.
Classic hard benchmarks.
Right. Then multi-hop question answering using Hotpot QA, tested on out-of-distribution sets like 2Wiki and Music. And we have function calling using the Berkeley Function Calling Leaderboard BFCL v4.
A very comprehensive suite.
And the policy backbones they trained are Qwen 3.8b and Qwen 3.14b, and they validated the approach on Llama 3.23b as well.
So mathematical reasoning is really the ultimate stress test here. In math, credit assignment is brutal.
Oh, for sure.
A single flip sign at step 2 of a derivation completely invalidates a brilliant 10-step proof that follows. There is no partial credit, which is why outcome-only RL struggles so much with it.
It's just a 0.
Exactly. But the results across all these domains are striking. Trace consistently beats standard GRPO, the prompt filtering PCL baseline, and even a random TreePO baseline.
We should quickly define that random TreePO baseline for people. That's an optimizer that builds trees, but it samples its branches completely randomly instead of using the V times 1 minus V predictor to target the high variance nodes, right?
Correct. It builds the tree structure, but without the intelligence of where to branch. And random branching often fails in long horizon tasks because the probability space of failures is huge.
Right, there are a million ways to fail and only one way to succeed.
Exactly. So if you branch randomly, you usually just find more failures, which gives you no contrast. By targeting the variance, Trace avoids that. On the Qwen 3.14b multi-hop QA benchmark, Trace improves average accuracy by 2.8 points over the competitive baselines under the exact same rollout budget.
Wow, 2.8 points just from smarter sampling.
Yeah, but the accuracy gains are almost a lagging indicator. The real star metric that proves the theory works is the effective ratio.
The effective ratio is the fraction of rollout trees that actually contain both successful and failed outcomes.
Right.
Because if a tree is all ones or all zeros, like we said earlier, it's effectively useless for gradient updates.
Exactly. And on the deep scalar mathematical reasoning task with Qwen 38b, the standard GRPO baseline had an effective ratio of 26.8%. Trace pushed that effective ratio to an incredible 60.6%.
Wait, 60.6%? Going from 26% to 60% isn't just an incremental bump.
It's a massive leap.
That means previously 3 out of 4 generated trees were going straight into the trash as wasted compute because they lacked contrast.
Yep, completely thrown away.
Trace is basically recycling your garbage GPU cycles into pure gradient signal. You're paying for the exact same amount of compute, but your optimizer is receiving more than twice as many rich, actionable preference pairs.
Now, we do need to address the cost of the predictor model, the v tilde psi, because nothing is totally free in machine learning.
Right. Running that predictor has to cost something.
The authors ran extensive ablation studies and profiled the runtime. The predictor they use is a tiny Qwen 3.6b model, pre-trained as a value network.
Ah, 0.6b is tiny.
It is. Because it's so small compared to the 8b or 14b policy models it's guiding, the overhead is minimal. The profiling shows that the predictor scoring takes less than 2% of the total wall clock runtime.
Less than 2%.
Yeah, while the actual LLM policy optimization and rollout generation takes up 66 to 75% of the time, less than 2% overhead to more than double your effective learning signal is a trade-off literally any ML engineer would take in a heartbeat.
I would take that deal every time. And there's an interesting dynamic with how that predictor behaves as the trajectory gets longer, right? Proposition 1 in the paper proves mathematically that the predictor's accuracy strictly improves as it sees deeper prefix histories.
It does. It acts exactly like an observer in a poker game.
Oh, I like that.
At the pre-flop, predicting the winner is incredibly noisy. There are just too many variables. But by the turn in the river, as more cards are revealed, the predictor's accuracy skyrockets.
Because the state space is collapsing.
Exactly. In the context of an agent, as it takes more actions and observes more of the environment, the predictor's estimate of success gets sharper.
That makes perfect sense.
That means the local branching decisions become highly accurate exactly when it matters most, deep in the trajectory where the fatal mistakes usually occur.
So what does this all mean? Reframing how we handle agentic RLVR sampling seems to be the ultimate takeaway here.
If we connect this to the bigger picture, it really is a paradigm shift. Historically, scaling RL meant just throwing more compute at the wall and asking how many independent rollouts can we afford to draw.
Right, just brute force.
Trace changes the fundamental question to where should we branch within the rollout tree? It takes scalable, cheap outcome rewards and transforms them into the kind of dense, stepwise preference signals that used to require expensive human process labeling.
It bridges the gap between the efficiency of outcome rewards and the density of process rewards.
It proves that we don't necessarily need more compute to train better agents. We just need smarter compute allocation. By treating the rollout budget as a resource to be dynamically invested in high-variance states, Trace extracts the maximum possible learning signal from the environment.
It takes a blunt instrument and turns it into a scalpel. Well, thank you for joining us for this deep dive on AI paper slop.
It was a pleasure.
But before we sign off, there is a fascinating implication here that extends beyond training.
Oh, definitely.
If this lightweight prefix predictor is so incredibly good at identifying the exact nodes where an agent's success is uncertain during the training phase, could we deploy this exact same v tilde psi model during inference to guide test time compute?
That is the million-dollar question.
Right. Imagine a deployed agent that monitors its own v times 1 minus v variance as it works on your prompt. An agent that only pauses to think harder or launch parallel search branches when the predictor flags that it has reached a high variance critical fork in the road.
It would be incredibly efficient.
It could optimize test time inference budgets just as beautifully as it optimizes training budgets, giving us agents that know exactly when they are confused and exactly when to spend extra compute. Ponder that implementation while you wait for your next training run to finish. We'll see you next time.